Welcome back. In this video, I will introduce various physical media that are used in computer networks as links. And I will also describe what happens to signals when they are sent over a link. We are going to focus on these three kinds of links: copper wire, fiber optic cable, and wireless. By the end of this video, you would know what are the commonly used links in computer networks and what are their properties, and you would also know how do signals get modified when we send them over a link. As we saw in the previous video on layered network architecture, the physical layer is the first layer of the architecture. The function of physical layer is to transport bits from one node to another. Even though computers exchange bits, physical media can only carry analog signals. It is the job of physical layer to convert digital data to analog signals that are suitable to be carried over a particular physical media. Links typically rely on electromagnetic field to carry signals, though there are other kinds of links that use different methods, such as acoustic waves and movements of molecules. We often categorize links according to the medium. The most common medium are copper wire, optical fiber, and wireless. Though all three can be found in LANs, almost all long-distance links and undersea cables are optical fiber. In addition to the kind of physical medium, another important link characteristic is the speed of propagation of signal through the medium. The speed of a wave is defined as a product of frequency and wavelength of the wave. The rate of oscillation of a wave is called its frequency, and it's measured in hertz. 1 hertz is 1 oscillation per second. And the distance between the adjacent pair of maxima or minima or any other equivalent point is called the wavelength, and it's usually denoted by lambda, and its unit is meters. We use this relation between speed, frequency, and wavelength to determine one of the third quantities given the other two. For example, suppose we want to know the wavelength of a 2.3 kilohertz wave through copper. Now note that people would use the term light to refer to electromagnetic wave. According to this formula, the wavelength is equal to the speed of wave divided by its frequency. And so this is going to be a speed of light in copper wire divided by the frequency, and that is equal to 2.3 times 10 to the power 8 meters per second. That's the speed of light in copper, divided by the frequency that is given to us, which is 2.3 times 10 to the power 3 hertz, which is per second, right? And per second unit here cancels, so you're left with meter, and what we get is 10 to the power 5 meters or 100 kilometers. We are going to discuss two kinds of copper wire, Cat5 cable and coaxial cable. Cat5 cables are twisted pair copper wires that are used in Ethernet. A Cat5 cable has these 4 strands of twisted copper wire. These wires are twisted for a reason. They are twisted to reduce leakage of energy through electromagnetic radiation. And twisting also reduces crosstalk between neighboring wires. And therefore, these twisted cables are, more immune to or better immune to external electromagnetic interference. And all in all, this twisting improves their signal quality. And because of that, Cat5 cables can go up to 100 meters. There are also Cat6 and Cat7 standard cables also used in Ethernet that provide better performance. In 10 and 100 Mbps Ethernet, only 2 of these 4 cables are used. One carries signal in one direction and another pair carries signal in another direction. In gigabit Ethernet, all of these 4 pairs are used. So there is some terminology that is relevant here. We call a link simplex if it can carry signal in only one direction, right? And one example is the GPS links. And then there are duplex links that allow simultaneous communication in both directions from one party, let's say A, and another one B. So simplex would only allow communication in one direction. So this is simplex. Duplex would allow communication in both directions simultaneously. And sometimes, duplex links are implemented as a pair of simplex links, as this example shows. And then we also have what we call half duplex links. And these links can transmit in either direction, but they can carry conversation in both directions at the same time. So in half duplex link, either A can transmit to B, and once it finishes, then B can send something back, but not simultaneously. And wireless links are usually half duplex links. Coaxial cable is another very common copper link. Coaxial cables have much better protection from noise than Cat5, and therefore they have much longer range. They can go up to 1 kilometer. They also tend to have more bandwidth than Cat5 cables. Coaxial cables have a stiff copper wire at the center, followed by an insulating material, followed by a mesh-like structure made of wire, and this entire thing is put inside a protective plastic sleeve. Coaxial cables are used for providing internet access by cable TV companies. The next physical medium that we will consider is optical fiber. Inside fiber optic cables, the signal is basically carried by a thin glass wire. This thin glass wire is surrounded by a glass shell, and all of this is enclosed in a protective plastic sleeve. A beam of light, when sent from a higher refractive material such as silica to a lower refractive index material such as air, tends to bend away from the direction that the beam was sent. And so in this figure, this angle beta 1 is greater than alpha 1. It turns out that as we increase this angle, this beam bends more and more. And there comes a point at which this entire beam is reflected back inside the material where it was sent from. And the angle at which this happens is called critical angle. And so if a beam is sent at a critical angle or at an angle that is larger than the critical angle, the entire beam gets reflected back in the material. And this phenomena is called total internal reflection. In an optical fiber, this trapped beam propagates by getting reflected from the walls of this thin glass wire again and again. And because of total internal reflection, the signal quality remains excellent for hundreds of kilometers. So these optical fibers tend to have very long range. Fiber optic cables also offer massive bandwidth. Even the low-end fiber link offers tens of gigabits per second to up to 1 terabit per second. The world record of highest or largest data rate achieved on an optical fiber is 172 terabits per second, and it was achieved in April 2020 by a team of Nokia and NICT in Japan. Because of their very long range and massive bandwidth, they are used in internet backbone. Their role in the explosive growth of the internet had been very, very important. Fiber optic cable is also used by internet service providers for high speed home internet access. That is called FTTH, short for fiber to the home. Some gigabit Ethernet LANs also use fiber optic links. Being made of glass, bending a fiber optic cable too much causes this optical fiber to break. On the other hand, compared to copper wires, fiber optic cables are much cheaper to manufacture, and they are also much lighter, and therefore they are more and more preferred over copper wires. This image shows the optical fiber undersea cables deployed all around the world. The undersea cables are fortified with many layers, including a layer of steel wires to protect them from corrosion and unintentional damage from ships and also sharks. The next physical medium that we will discuss is wireless. Wireless links are increasingly replacing wired links in our homes and offices. This is a very simplified version of electromagnetic spectrum usage. The commonly used wireless systems such as Bluetooth, Zigbee, Wi-Fi, and cellular networks operate in this microwave band. This band ranges from about 300 megahertz to 300 gigahertz. Coaxials operate in the lower end of this spectrum, ranging from few hundred kilohertz to few hundred megahertz. And fiber optic cables operate in this band around hundreds of terahertz. Conventionally, the spectrum band of fiber optic systems is stated in terms of wavelength and not frequency. Fiber optic cables operate in the range from 1260 nanometers to 1675 nanometer band. It is important to note that the use of electromagnetic spectrum is regulated by governments. We are not free to use a spectrum at our will. Because of very high revenues, governments tend to auction parts of the spectrum to telecom providers. However, there are certain frequency bands that can be used without obtaining license. The industrial, scientific, and medical bands, known as ISM bands, can be used by anyone without obtaining license, provided the transmit power is kept within prescribed limits, and then there are certain other restrictions that have to be obeyed. The ISM bands are shown here. So there's one that operates around 902 to 928 megahertz. There is one that's 83.5 megahertz wideband at 2.4 gigahertz. And then these are three bands collectively known as 5 gigahertz bands. This term last mile links refers to the links that connect internet access point at customer locations to the internet service providers. The most common last mile links are cellular, DSL, cable TV, and fiber. The data rate of cellular networks improves by 1 to 2 order of magnitude with every new generation, which comes every roughly 10 years. 2G networks had data rate of tens of kilobits per second. This was improved in 3G networks to hundreds of kilobits per second, and further in 3.5G networks to tens of megabits per second. 4G is supposed to give hundreds of megabits per second, but in practice we get a lot less. 5G is promised to give tens of gigabits per second. It would be interesting to see what 6G networks will provide. In addition to bandwidth, every new cellular generation has been expanding the set of services it supports. 1G provided analog voice service. 2G improved it and provided digital voice and text services. 3G added mobile data service capabilities. 4G improved 3G data service to the point that high definition streaming is now possible. 5G will add to 4G capabilities by supporting new applications that require real-time deterministic services like remote surgery or industrial Internet of Things and vehicular networks and so on. On the wired side, the bandwidth ranges from tens of kilobits per second to few gigabits per second. Dial-up and ISDN are of historical interest. Back in the days, they used to give from tens of kilobits to hundreds of kilobits per second. DSL gives up to 100 Mbps, and cable can give up to tens of megabits per second. And as we have discussed before, fiber is capable of delivering up to a few gigabits per second. Now we shall briefly discuss how signals get affected when transmitted over a link. As Fourier showed in 1807, any periodic signal can be decomposed as sum of series of sines and cosines of different frequencies. When a signal passes through a link, it attenuates different frequency components differently. The range of frequencies that get passed through a link is called its bandwidth. Note the meaning of bandwidth is not data rate here. It is the difference in the frequency. It's a maximum frequency minus the minimum frequency. Often the bandwidth of a link is limited by using some kind of filter that allows a certain range of frequencies to pass but block the rest. And therefore, the range of frequencies that can pass need not start at 0. When a link attenuates the different frequency components of a signal differently, it results in the received signal getting distorted. Let us consider what happens when we send letter B over some link. The ASCII representation of B is 011000010. A binary signal would encode B as this waveform. This graph, or rather this figure, shows the amplitudes of different harmonic frequencies of this waveform in time domain. These 4 figures show the distortion that results when the link would pass only first few harmonics and block the rest. This is reconstruction of the signal when the link would pass only the first harmonic. This one when the link would pass the first 2 harmonics. This one when the link would pass the first 4 harmonics. And this one when the link would pass the first 7 harmonics. In these first 3 cases, the reconstructed signal is too distorted for us to recover the bits that were transmitted. We can recover the sent bits from this last figure, that is obtained by reconstructing from the first 7 harmonics only. One can correctly infer that 0, 1, 1, 0, 0, 0, 1, 0 were the bits that were sent. And therefore, although in the Fourier spectrum we have infinite frequencies, but in practice only a finite number of harmonics suffice to recover the sent data. In addition to getting distorted, the received signals also get degraded due to attenuation and noise. Every link dissipates energy. This results in attenuation of signal amplitude, like the amplitude of 1 getting decreased and decreased as the signal goes farther and farther on the link, to the point where 1 is not distinguishable from 0, and this limits the range of a link. The signals also get degraded because of noise. This noise could be thermal noise, noise from electronics circuitry, and external interference like electric spark and so on. And noise gets added to the signal. If the noise level is too high, the sent data may not be recoverable from the received signal. Take the example of this waveform. In the presence of noise, the resulting signal would look like this, could look like this. And this, on top of decrease in amplitude, can make recovery of the sent data difficult. In case of wireless links, the impact of attenuation and interference is far more severe than wired links. Wireless transmissions attenuate at the rate of at least the square of inverse of distance. In practice, in urban environments, this exponent is usually between 4 and 6. And this leads to the short range that we see in case of wireless links. Signals transmitted through wired links or guided media in general remain largely confined within the medium. This is not true for wireless links anymore. The effect of crosstalk in wired links is minuscule as compared to the interference caused by simultaneous transmissions over wireless links. Simultaneous transmissions may cause a receiver to fail to decode the sent message. This phenomena is called collision, and this is highly undesirable. Wireless signals can get reflected from surrounding objects like buildings, walls, fences, ground, etc. So consider here the sender is sending to this receiver, and so there is a direct beam that goes from the sender to receiver. Now this signal can get reflected from this house and reach the receiver through a different path, and then there may be other obstacles or objects that reflect it, and so the signal from S to R reaches R through different paths, and therefore it reaches at R at different times, and this difference in time causes shift in phase. This phenomena is called multipath, and the result of that is that at the receiver you could have a situation where you have a constructive interference, means these two beams that arrive at R, where one signal is stronger, other is weaker, but is still in phase, and therefore the overall sum is still fine. It's bigger in amplitude, nothing harmful there. And then there may be a situation where these two signals arrive at R completely out of phase, and therefore when they combine, they basically cancel, and there is no way that a receiver can decode what was sent. So this effect of multipath is location dependent. If R moves to some other location, again there may be a situation when this destructive interference does not happen, and so this multipath causes the receiver to fail to receive signal at certain locations, and then it's able to decode the signal at certain other locations, and this is unique to wireless links. These are some of the main points of this video. Fiber optic cables offer massive bandwidth, and they have very long range, and they are used in long distance links and undersea cables that carry internet traffic. Signal propagates through links at the speed of light in that medium. Electromagnetic spectrum usage is regulated by governments, although there is a set of bands called ISM bands that are unlicensed, and anybody can use them without getting license. Fourth, signals get attenuated, distorted, and added to noise when they are sent over a link. And finally, we saw that wireless transmissions suffer from strong attenuation, interference from other ongoing transmissions nearby, and multipath effect. For further reading, I recommend Wikipedia articles on infrared and satellite links. We have not covered these two. There is a very good discussion of satellite links in Tenenbaum and Weatherall's book. It's in Chapter 2, Section 4. In Peterson and Davies' book, what we covered, a portion of that appears in 2.1. And much of what we discussed in this video is in Tenenbaum and Weatherall's book in Chapter 2, Sections 1 to 3. Here is a short quiz for you to test what you learned in this video. You might want to pause before looking at the answer. The correct options are A, B, and F. A is correct. Link is a physical medium. B is also correct. Data must be converted to analog signal because that's what can travel in a physical medium. C is wrong. Wi-Fi refers to wireless standard IEEE 802.11 and therefore this is wrong. D is wrong. Speed is not frequency divided by wavelength but frequency times wavelength. E is also wrong. Wireless signals attenuate as 1 over distance to the power alpha, where alpha is greater than 2. It's equal to 2 in free space. And F is correct. ISM bands do not require obtaining license prior to operating. That's all in this video. See you next time.